Dear learners, welcome to the NIOS studio. Today, the topic that we are going to deal is fluids and the properties of fluids. And the main objective of this topic is to make the understanding of fluids, make the understanding and the calculation of hydrostatic pressure. Now, what is actually a fluid? So, it is nothing but the name given to a substance which begins to flow when an external force is applied on it. Therefore, we can state that whatever the substance it is, when an external force is applied and it begins to slide or to flow, then we can say yes, it is a fluid. For example, water, a honey, the liquid metal which is known as mercury, they all are existing to be a fluid. First, we should know that what is actually a pressure. I have this paper which is a simple A4 size sheet folded into 4 folds, along with whom I have 2 types of pin. One of them is a flatter pin and the other is a very sharp pin. The flatter pin have a large area comparative to the sharp pin. When we try to put a pressure on this paper, I need to apply more force. Even then, the flatter pin does not pass through the paper. Whereas, while doing the same thing with the sharp pin, if I try to apply a force with this pin, it can easily pass through the folded sheets. From here, we come to know the lesser the area, the more the pressure. And this more pressure can easily be attained by using a simple pin. The most common fluid that exists in day-to-day life is water. So, we will take the example of water and try to explain the properties of fluids, that is hydrostatic pressure. How to analyze that what amount of pressure is exerted by a fluid? First of all, the normal force is exerted by a liquid at rest. The normal force is also known as thrust. Therefore, we can say that the normal force exerted by a liquid at rest per unit area of a surface in contact with the fluid is called pressure of liquid and most famously known as hydrostatic pressure. The pressure is given by force per unit area. The emphasis is that the implied force is normal to the surface of an object which is in contact with the fluid. In this diagram, we try to show the structure of a dam where the water is filled up till a certain height. As you can see, the lower structure of the dam is much wider, and as we increase the height, the structure of the dam gets narrow. Why is it so? The answer lies that the pressure increases with the depth, and you can see the lower structure of the dam is made wider comparative at the height. Since the height increases, the widerness, or can say the structure of dam, becomes narrow. In this diagram, we try to explain that when a jar is taken which is filled with water till a certain height and a cube having a symmetric surface is dipped into that water, the water implies normal thrust on each surface of that cube, where F is a normal force and the surface area is given by the capital A of an object which is in contact with the liquid. Now we can demonstrate the same example that has been denoted by the diagram by using a glass filled with a water till a certain level. When I release this cell on the surface of the water which is at rest in the glass, it will dip till the bottom of the jar. Now you can see the cell is not moving anywhere, and through this we can analyze that the water which is at rest is implying the force at every side, at every surface of this particular shape. Through this, we confirm that yes, when the liquid is at rest, it implies pressure in equilibrium condition which is on every surface of its shape. The units of pressure is given by Newton per meter square or Pascal, and the dimensional formula is given by m L minus 1 T minus 2. Next, we will see that what would be the hydrostatic pressure at a point inside a liquid. We will consider a liquid in a container and an imaginary right circular cylinder of cross-sectional area which is denoted by capital A and the height h. We had plotted a diagram giving the condition of a hydrostatic pressure. The cylinder in this condition in a state of equilibrium. Here we can see when the cylinder is in a equilibrium condition, the pressure exerted by the upper pressure and the upward thrust by the liquid is at the lower bottom side. Since an object is there which is having its own height, will also be having its own mass, which is attracted by the gravity. Since it is in equilibrium condition, therefore, we can say that the total force implied is equals to 0. At the upper side, the total force is given by F1, and in the same direction, mass into gravity product is given, and from the lower side, an upward thrust is implied given by F2. Now, in terms of pressure, we need to elaborate this equation, and force is given by the product of pressure into area. Mass is nothing but given by the product of density of an object into the volume, where the volume can also be elaborated in the form of the product of area into height of the cylindrical object. And minus F2, as you can see from this equation, area is a common term which will left us. This term G is due to the availability of the weight. Therefore, we need to multiply G in this equation also. And the left over term is given by this. When we try to solve this equation, the answer is given by therefore, the pressure implied by the liquid is given by the pressure difference for the upward thrust implied by the liquid, the pressure at the upper surface area, which is the solution for the product of height of the cylindrical object, the density of an object, and the gravity implied over to the object. We got the conclusion that pressure difference is given by H into rho into G, and it is due to a fluid which increases linearly with the depth. If we consider the upper face of the cylinder to be at the open surface of the liquid, therefore, I can say the P2, the upper surface pressure, is replaced by the pressure of the atmosphere. And again, by considering the same difference, you will get the same answer, which again depends on the height of the object. Pressure does not depend on the shape of the vessel. And to prove it, we are showing this diagram. Here you can see there are different shapes of the vessel, but the level of the water lie to be same. And we know that the pressure is given by the product of height, the density of the liquid, and the gravity. Therefore, in all the four apparatuses, the pressure is same. We had already denoted the amount of pressure at certain point, and they are denoted by the points A, B, C, D, and the E. And at those points, the amount of pressure implied by those liquid are same. Till now, what we had learned, that hydrostatic pressure existed with the variation of height, and it also depends on the lower and the upper surface area of an object, and pressure does not depend on the shape of the vessel. Thank you. Dear learners, welcome to the NIOS. Today we will be dealing with the fourth part of the properties of fluid, and today we are going for the Pascal's law, one of the most important law when we deal with the fluids. Here we will be able to understand that what actually Pascal law states. and what are the different applications that we are using in our day-to-day life. Through this diagram, you can see that on one side of the platform, a man is standing, and on the other side, the car is placed. But both are connected by the fluid. Obvious, the mass of the man is very low comparative to that of the car. Then how does he able to lift a car with very ease? How does it work? Today we are going to learn this concept. Here we analyze the smaller force is exerted on one side, and on the other side the area and the force is large. It is implied by using a Pascal's law. What does it state? It states that the pressure is applied at any part of an enclosed liquid. It is transmitted undiminished to every point of the liquid as well as to the walls of the container. Means there will be no loss of pressure anywhere inside the container. Now look at the smaller sides. At the smaller side, we are having a pressure given by F1 by A1, the ratio of both the quantity, which must be equal to the pressure on the larger side, which is given by F2 A2. We already know that the transfer of pressure is undiminished. That's why both the pressure are equal to each other. And it is then very easy to lift any heavy object by using a very small amount of force on one side. Now, according to Pascal, we had already explained. Now it is denoted mathematically as the last of the equation, F2. F2 was the amount of force which was exerted on the larger side of the area. Here, the pressure is exerted in terms of the smaller side. So the pressure is given by F1 A1, and for the larger side is given by A2. Therefore, when both the quantities are equal, and by cross multiplication the two equations, we got this result. And this is the actual mathematical concept behind the Pascal's law. This law is also known as a law of transmission of liquid pressure. Now, turning towards the application, the basic uses are the hydraulic press, the hydraulic balance, and the hydraulic jack. The very first application that we had already shown you, hydraulic jack. Here, we again gave the demonstration in a very detailed that how do we get an amount of small force on one side of the tunnel and the amount of larger force on the other side of the platform, which is connected through the liquid. And we are easily able to lift the car over to placed, which is over to the platform. So the force in small cylinder must be exerted over a much larger distance. A small force exerted over large distance is traded for a large force over a small distance. This is somewhat an inverse case. So a small force will turn out to be a larger force on the other side. Then the hydraulic brakes. The hydraulic brake is used basically in the vehicle or the four-wheelers, where the pressure applied gets transmitted through the brake oil to the piston of the slave cylinders, which in turn pushes the brake shoe against the brake drum in the four wheels simultaneously. Then only the wheel stops rotating and the vehicle comes to stop. Here is a demonstration. The foot shows the brake pedal, which is connected to the master cylinder where the fluid or the brake oil is inserted, which is interconnected to that fluid, the caliper and the disc. When this caliper or disc gets open up, it attaches to the rotation of the wheel and it gets stopped. So till now we had learned that what is actually a Pascal law, what are the applications of Pascal law. Thank you.